At the conclusion of this, in 2 or 3 lessons, we will have completed half of the course. The test is Thursday, week 7, which is a Monday's timetable, and it is on topics 5 to 8, including this topic. It's the 13th. Yes, mate. Picture a magnetic field, something like this. We draw lots of uniform magnetic fields. Here we have a uniform magnetic field. We only look at uniform magnetic fields. They're much easier to draw and also to understand. It's a simplified version. Charges in magnetic fields. I might send a charged particle, and it could be positive, through this magnetic field at some speed v. You're going to find shortly that its velocity does matter. As to the force it experiences, we know that this charged particle is going to experience a force due to its interaction, or its magnetic field's interaction with this external magnetic field here. So B, actually B, this is an external magnetic field. And if I were to draw the magnetic field here, I use the right-hand rule, point my thumb in the direction of the flow, and I see that the magnetic field due to this charged particle is something like this, rotating around it. And I want you to consider that this is a bunch of charges moving with speed v. If we have a bunch of charges, we have a group of charges moving at speed v, then we have what is called a current. Okay, this could be called a current. What happens if we... what force is this charged particle, or this current of charged particles, going to experience? Which one is... No force. It won't experience a force. Why is that? Yeah, it's moving parallel to the external magnetic field. So I'm sorry, I don't understand, Josh. Should it be going right-hand rule? Using your left hand. Yeah, use your right hand. Definitely use your right hand. It's a common mistake to make. It's okay. Lots of people have made that mistake in the past. Don't do it in the tests. A charged particle moving parallel to an external magnetic field experiences no force. No force. And I'll show you a picture in our textbook. Actually, it's not in this part of the textbook, I don't think. No. If we go back here, what's going on there? Oh, I see. Magnetic fields. Have a look at this diagram. Essentially what we've got here, it's the same thing. So you can imagine this magnetic field is into the page, and this current here is also into the page. It's exactly the same orientation except twisted to 90 degrees as this situation here. Can everybody see that? They can exist in space together. Okay. The magnetic field due to this uh, current, this moving current, can exist in space with this external magnetic field, the crosses there. Okay. Let's look at a different situation with electrons. We can fire electrons with an electron gun. If we get time, I'll show you one, an electron gun. If you have the old style TV, then you have an electron gun in your house. Essentially, yeah, the back of the TV, in the back of the TV is an electron gun. It fires electrons at that screen, at that phosphorus screen, and the phosphorus screen lights up when the electrons hit it, and that's how we see a pixel. So this might be electrons. This is an electron current. Here, and I'm going to draw a magnetic field now at 90 degrees to the one I just drew then, before. I'm going to draw it going into the page. Now, this current of electrons, this flow of negative charge, is going to experience a force. Does anybody know what force it experiences? Have a think about that. If a charged particle moving with speed v downwards, moving with speed v and charge q, yes, flow of negative charge there, conventional. There's a couple of ways you can do it. I'll show you in a second. Yeah, I tend not to do that. There's two ways that you can do it. Have a look here. In this situation, I'm going to use the right-hand palm rule. Right-hand palm rule. And because we know conventional current is the flow of positive charge, I'm going to point my thumb in that direction. Because if the flow of negative charge is to the right, then the flow of positive charge is to the left, you could say, or opposite that. So that would be my thumb. My fingers then, because this magnetic field, this external magnetic field is going into the board, denoted by these crosses going into the board, then I point my fingers in this direction. So I'll just do this, fingers. For the right-hand palm rule, thumb, fingers. Which way is my palm facing? It is facing downward. The electron experiences a force downward, and so I could say this. Now we're going to see that in fact this is true shortly. That would be that is a path that the electron beam could possibly take. could possibly take. You might notice that I've drawn something that looks reasonably circular. The force, I'll actually draw the force in yellow. Force down the page. You'll notice in a second, I'm jumping the gun here, but imagine that's the vector, that's the velocity vector of that electron beam there. Of course, the force is downward, and so the electron beam is going to move downward. Have a look at the velocity vector here. If I were to draw it in there, and then if you were then to draw, you then to show the force, so thumb in the direction opposite the direction of the motion, or opposite the direction of the velocity of the electron beam, and fingers still in the direction of the magnetic field, then we'll see that the force is always at right angles to the velocity. Always at right angles to the velocity. So if we have a constantly changing velocity because it's changing direction and a force at right angles to it, then you'll know from uniform circular motion that we actually have uniform circular motion. Okay. That's a pretty sad arrow. Force, yes I can. By the right hand, I should use capitals for this. Right hand palm rule. The force that the electron beam experiences is always at right angles to the velocity. So the force that the electron beams experience is always at right angles to the velocity. As a result, we will see motion. And that's assuming that the magnetic field is, if we make the magnetic field such that the electron beam can move in a circle, then it will. Okay, so if we made the magnetic field all over the place here, that electron beam could actually move in a circular pattern if it wanted to, uniform circular motion. At this stage, you could say in this situation here, it's just going to move with a circular path until it leaves the magnetic field again. Okay. We know that the force it experiences is this: F is equal to Q V B sine of theta. I'll state that now and then I'll explain it. QVB sine theta. How do we get this? How to get this? Think of the magnitude of the current could be defined as I equals the charge per unit time. And what that means is that's the rate of flow of charge, delta Q on delta T. If a current of 2 amps, as an example, current of 2 amps is moving past the point each second, we say that 2 coulombs of charge past that point each second. Current of 2 amps is moving past the point each second. Or actually, it's probably better to say that what I've written, the current of 2 amps is flowing in a circuit. We say that 2 coulombs of charge is passing a point each second. Have a look at this situation now. So I'm saying now that I is delta Q on delta T. Picture a magnetic field. I'm going to draw it in a different orientation to what we have done in the past, just so that you don't only know into the board and to the right. The magnetic field can go in any direction oriented in space, of course. And I put a current carrying wire in that magnetic field. I can do that. We're only interested in this area in here because that's delta L, isn't it? Delta L between those 2 points there. It's the portion of wire. It's the portion of current carrying wire that's inside that magnetic field. And we say the current element is I times that delta L. We learned recently that the force on that current carrying wire is I delta L times B times sine of theta. This is, you could say this is theta. And you could say that the green, of course, I'm drawing the magnetic field always green just for consistency's sake. That's B. then we know that the force that that portion of the wire experiences in that magnetic field. If I substitute for I, this delta Q and delta T, and delta L, what could I substitute for delta L? Well, delta L is just a distance, isn't it? From velocity equals distance over time, we see that distance equals velocity times time. And so I'm going to substitute that in. F is equal to delta Q on delta T, substituted for I, times VT, substituted for delta L, B sine theta. We can cancel some stuff, or namely just the time there, they cancel out. And we're left with our new formula for the force in relation to the charge, Q, the velocity of the charge or the flow of charge, magnetic field, and then the angle that that magnetic field makes with that flow of charge. F is now equal to QVB sine theta. Put a box around it. What does the box mean? Important. Well, I should do this then. Everything's important. Okay, it's all important. So what you'll find in your, if you do occasionally have a look at your equation set, the equation set that you receive for every test and exam this year, you'll notice that most of these are actually in there. And so I say they're important, I put a box around them, but you get them anyway. Every test and exam. Every test and exam you'll receive that formula sheet. So from that formula we can say that the force is velocity dependent. And direction of the force is always perpendicular to the velocity. Oh, I have a question for you. Next page. I'll put it back up in a second. Here is your first task today. Before we go on with that, any questions here? Firstly, I think, is there anything that I've stated that's a little bit unclear? Sometimes it's difficult for me to see the problems that people have because I've seen all of this stuff several times now. So I forget very quickly where difficulties are. You need to remind me of those difficulties that people have. That's important. Can we move over to the question now? question 1 says the magnitude of the force on the electron. Of course, we've just learned a formula that says that force is equal to Q times V times B sine of theta, which is equal to V 2.00 by 10 to the 6. Question? Okay, yeah, so have a look here. When I like to draw a triangle. What am I interested in? I'm interested in that component. There's 2 components here. Let's draw them in. And this is how you're sure. There's the component that's perpendicular. No force. No, I'm not interested at all. That's the one that I'm interested in, isn't it? That component of that current. And it would be like this. Okay? It would look like that. So if theta is in here, opposite over hypotenuse, I'm going to say that's 40 degrees. In this situation, let's say the 50 degree one. So somebody's saying, do we use 50 degrees or 40 degrees? Well, this is how you work it out. Yeah, look. There's your 50 degrees in there. That's going to be adjacent over hypotenuse, so it's going to be cos 50 in that situation. Because you're interested in that component that is perpendicular to the magnetic field only. Forget about this guy. You don't want to find that guy out. All right? Why can't it just be easy? I guess that's yeah. This is the easy part. What you're going to find if you guys go on to study university physics, you're going to get to university, and your university lecturer is going to say, okay, everything you've learnt so far is not entirely correct. Here's what it really is. And then when you finish that, they'll say, right, not all that is entirely correct. Now you learn this. But by the time you learn that third part, if you get that far, it gets harder and harder and harder. You need to learn this stuff to be able to understand the next bit. Okay, B is 4.5 Tesla times sine of 40 degrees. And my book says 9.26. It's a force, so it is measured in newtons. It's measured in newtons. Question 2, so that's the magnitude of the force. Direction, how do we find this direction? Okay, so I drew some vectors in here before, and I know that this vector here, this one, or this one here, is the one that I'm interested in, that one that is perpendicular to the magnetic field. That's the component of this velocity that experiences the force. But it's a flow of electrons, which means that the vector, you could say, flow of positive charge for conventional current is this vector. I'll draw it in. Hopefully I won't make too much of a mess. Is this vector here. And let me put an arrow on it. That there is conventional current. There. Okay, so this one now has a component that is perpendicular to the magnetic field. And I'll draw that in. It actually, here it is here. I'll draw it in here. There it is there. It actually goes opposite the one that I draw, but it's still perpendicular to the magnetic field. So I'll draw its arrow on it. I'm making a mess here. This is the one that we're interested in that direction. That's the direction in which I'm going to point my thumb down the page. I'm going to point my fingers in the direction of the external magnetic field. And if you do that with your right hand, your palm will be facing us or out of the page. Out of the page. Okay. 3. Did anybody do 3? What would be the force of an electron moving from left to right as it enters the field? It will be, the flow of charge will be parallel to this external magnetic field, so no force. What's that? 4. What would the force of an electron moving down the page as it enters this field? Okay, so straight down the page. Yeah, they want you to actually do a calculation for that, guy. So let's draw that in. Here's an electron, and all of a sudden, we've fired a beam down the page. What's the force that experiences? What angle has it to the magnetic field? Sine 90 equals 1, doesn't it? F equals QVB times sine of 90, which is equal to 1. The charge is 1.6, 10 to the minus 19, times 2.00 by 10 to the 6, times 4.5 Tesla. I get a value of 1.44 by 10 to the minus 12. Newtons. In what direction does it go? Into the page this time, isn't it? Because I'm going to point my thumb up. My finger's still in the same direction of the magnetic field, and I'm going to see that my palm points into the page. Question?
Is that a similar question to what would be in the test?
It could be. I didn't understand the question. Is that Dylan? All right, yeah. I'll give you some hot tips on the test. Anything could be in it in chapters 5 to 8. Extended response, chapters 5 to 8. Yeah, good question about the extended response. I'm not sure. No extended response. Maybe. I'm thinking about it. I have another question for you. E equals delta V on D. So delta V is 850 volts, and the distance is 5 centimeters, 0.05. We're going to put it in SI units for physics, of course. And we're left with a number 1.7. Yes, 1.7 by 10 to the 4. Of course, that's newtons per coulomb or volts per meter. I'll say newtons per coulomb. Okay. have a look at this. Let's look at the forces that a charged particle experiences. Because of the magnetic field, if you put it, it's a positively charged ion. So it's going to feel a force up the page, isn't it? Can you see by the right-hand palm rule? It'll experience this guy here. Okay, oops. And because of the electric field, it's positive. It's going to feel a force down. And yeah, that's right. The only way that it goes through undeflected, if they are equal, i.e. no net force on the charged particle. There are forces, but because they're equal, it's the same as us sitting on the ground here. There are forces on us at the moment. Shh, please. There are forces on us sitting here at the moment. One is gravity that's pulling us down. That force of gravity, that's our weight. And luckily for us, the floor is pushing up with equal and opposite force. And so we don't go anywhere. Same with these positively charged particles. So I can write a mathematical expression for that. I can say the force because of the electric field is equal to the force because of the magnetic field. But they equate to different things. F equals EQ on this side, and F equals QVB on this side. There's our value that we want, the V. We want that, don't we? Straight away, we see that the charge doesn't matter, and that's why they don't give it to us. We're left with from that V is equal to E on B. Yeah, this is the long way, but the other long way. Oh, okay. But I want to. Part of the reason why sometimes I tend to take the long route is because it's more explanatory for those students that are having difficulty with this. E, of course, we calculated 1.7 by 10 to the 4. Is this for you guys at the front? Yeah. Okay. And B, they give us 1.6 Tesla. Tesla is the SI unit for magnetic field, and we end up with the force. Yeah, 1.06. Sorry, the velocity is equal to 1.06 by 10 to the power of 4 meters per second is what you should have got. What is their speed? So I've said that's velocity, of course. If you wanted to say their velocity, then you'd have to give a direction. That's why they ask what is their speed. Question 2 says, describe the path of the ions which were travelling at a speed less than that found in 1. Well, it will be affected by... Shh, please, people. This is key to your understanding. You follow where we're at. We know... Shh, thank you. Will. We know that the force due to the magnetic field is dependent upon V. So if V is reduced, what happens to the force due to the magnetic field? Because they're proportional, aren't they? Okay, well, I better put it down with 2. Question 2. F sub B is proportional to V. So if V is reduced, so is the magnetic field force, or the force due to the magnetic field, and we have a resultant electric field force, which is down the page, and we'll see this. So I'll actually write part 2 up here in orange. 2 looks like this. We'll have this situation occurring. Okay? because the electric force results. Describe the path of the ions which are travelling at a speed greater than that found in 1. Well, then we're going to see 3. We're going to see the magnetic force increase, therefore wins over the electric force, and we'll see that sort of path. Okay. We better say something about that. If sub B is velocity dependent, F sub E is not, if we reduce V, we will reduce F sub B. And so we will have a net force due to the electric field. Any questions there from people before we move on and finish this topic? We'll just have the application to look at. Have a look at this diagram here. We have a charged particle moving. We're saying that it's positively charged, moving with speed v. As it moves into this magnetic field, this external magnetic field, which is denoted by the crosses here, it experiences a force at right angles to its velocity, and of course, circular motion ensues. So I think that's reasonably easy to show, and we did show that before. I'll just repeat it here. Because the charged particle experiences a force which is always at right angles to its velocity, it will move in a circular path. I hope everybody can see that reasonably well. It's flow of positive charge. I'm going to point my thumb in the direction of the velocity, of course. Point my fingers in the direction of the magnetic field, so into the board, and I can see my force is up the page there. It's that way there, it's that way there, it's that way there, and it's that way there. And we have circular motion, or a circular path. So remember, from uniform circular motion, the centripetal force is equal to because we have a centripetal force here. It's a force directed to some point in the center here. Of course, it's always pointed to the center of this circle. Remember this. You should do because you've been studying so hard. FC equals centripetal equals mv squared on r. And the force due to the magnetic field is equal to Q times V times B, because the particle is moving at right angles to the magnetic field, so we don't have to put a sine of theta in there. We can equate these. You know what I'm going to do now. I'm going to say bring that here and bring that down here. mv squared over r is equal to qvb in this case, and solve for r. Okay, so I'll move the r up here, take the qvb down there, but one of the v's goes, so we get r equals mv over qb. That gives us the radius of the circular path. A question for you. Oxygen ions carry a negative charge equal to 1 electronic charge. Enter a magnetic field of strength 1.5 Tesla at right angles to the field. The ions have a mass of 5.31 by 10 to the minus 26 kilos and a speed of 5.2 by 10 to the 6 meters per second. Find the radius of the path travel. Everybody can do this. I'm not going to ask you to do it because, well, before me, you can just follow me along this one. Let's picture first. I always like to draw pictures to picture what's going on here. Here's a magnetic field. I'm going to draw, actually we'll draw out of the page this time because this might come up. This is, imagine a magnetic field out of the page. It may be depicted like this. We're always drawing into the page. And I'm going to send oxygen in, and they're negatively charged. O minus, fire them in there at right angles to the field. 1 negative charge, electronic charge, so Q is equal to what? 1.6 by 10 to the minus 19 coulombs. R equals mv. Always state the formula that you're using or you're going to try and use, mv over qb. The mass they give us, 5.31 by 10 to the minus 26 times their velocity, 5.2 by 10 to the 6 meters per second. Quite a high speed. Q is 1.6 by 10 to the minus 19, and B is 1.5 Tesla. Type it into your calculator. It's a good idea for those people that don't use their calculator a whole lot to put that in there now. Put these values in there. Make sure you get the same number that I do. 1.15 by 10 to the minus 1 meters. The book says, which of course is 10 to the minus 1, 11.5 centimeters. Different answer, yes. Okay, so They're a big. It was what? Oh, 1.15 meters. The book could be off. Yeah, they often are. So you're only out by power of 10. You've got 10 to the power of minus 19, 10 to the power of minus 26, and 10 to the power of 6. You times it by 1.5. That shouldn't matter anyway, really. Okay, we'll go with you guys. Well, let's have a look. Let's have a look. 5.31. This just the reason I don't do this all the time is because it takes me so long. Minus 26 times by 5.2 to the power of 6. Am I going to put a? I'll put divided by. I'll put a bracket around this. 1.6 minus 19 times 1.5. Boys, no singing in here, please. 1.15 meters. That's what I get. Okay. So let's correct the book's mistake. Do you know we received a letter recently apologising for the book's mistakes? Why? Yeah, it's good. It actually keeps us on our toes, doesn't it? It's good for us. There we go. Yeah. It's good. It's a good idea. Example 4. This one's for you. And then, believe it or not, we've actually moved through this topic in no time. That's good. We've just got to do the application. Bainbridge mass spectrograph is used to determine the mass of zinc ions. They have a positive charge. Zinc ions enter magnetic field 1.8 Tesla with a speed of 4.2 by 10 to the 4 meters per second, and they move in a circular path of radius r equals 1.7. What is the mass of the zinc ions? This Zn with a little plus up the top, what does that denote? Yeah, they've lost a single electron, haven't they? So they still have a 1.6 by 10 to the minus 19 coulomb charge. They do. We can finish this very quickly. R equals mv over qb. Q for Zn with a little positive. That means it's lost an electron, so equal to 1.6 10 to the minus 19 coulombs. We'll rearrange this for the mass. Mass is equal to RQB on V. And then it's as simple as plugging it in, putting in your values, equating it. The mass is equal to 1.17 Thank you.